starting the recorder right now, so it is recording. All right, so we have a few ways to proceed today. So you guys can help decide how you want the class to proceed. We can talk about the exam, or we can start on a new topic, with the class material. So which way do you guys want? The exam? Okay. Any other opinions? Okay. Okay. All right. Let people trickle in. Okay. Well, people are not supposed to be trickling in. Okay, I take it back. They're supposed to be trickling in like 10 minutes ago. All right. Okay, so we can go over the exam just a little bit. Okay, let me go find it first. So that would be uh, almost there. 310. And this is the other class, so I'm gonna use the other class's ID, like this one. Okay. All right, so this is the exam that you took, and we'll start with question number one. So the question number one for this semester is actually shorter compared to the one before, which is a good thing and a bad thing. It's a good thing because it won't take you as long to answer question number one. It's a bad thing because each point or each line carries more weight. So that means the chances of quote unquote averaging out is not as good as the one before. So it's good and bad at the same time. So we can go over this a little bit, and let me see if I can record the answer. Let me get my mouse pad. There we go. All right. All right. So this one is set up differently in terms of the logic, but it is still testing you about the same kind of material. All right, so we have no need to explain blah 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 all the way up to 11. So that means the first thing we have to answer is on number 11. This is question number one, part 11. All right, so part 11 says the negation of x1 and y1, or the negation of q1 and t1, needs to be a zero. So the first thing, is to recognize what this is about. Okay, the first thing is to recognize. You can tell from here it is just T2. Okay, so you can recognize it too. But I can tell from the expression by itself here that it is T2. That helps me to locate the actual reference earlier. So I'm gonna say, okay, maybe one has to do with it. And then the other thing is we also need to know, what do we know about T2? Ah, number 9 says that. So that means, 1 and 9 together is enough to explain number 11. All right, so we move on to number 12. Number 12, says no need to say anything, so I'm going to skip over to number 13. All right, number 13 says, how do we know for sure that the negation of x1 and y1 is false? Well, that's directly coming from 11 alone. Okay, we explained the logic of this kind of reasoning before. Okay, so that's how we apply that. Number 14, same thing. Okay, so number 11 again. Number 15. Number 15 is directly, okay. So number 15 is directly because of 14, but you also need T1 being 1, which is 12 to support that. Okay, are we doing okay so far? Okay. So the test that you have may not have all of these things listed in exactly the same order. So I can see some people going like, oh, so that is what. Yeah, I generated like, different variations of the same thing, except things are sequenced, differently. Okay. So number 6, but they have the same statements, okay? Exactly the same conclusion, exactly the same statements, except the sequencing is different. So number 16 is so we look at the exclusive or between x1 y1, that would be q1. That's the definition of q1. So that means I know what I'm looking for, which is number 4. Okay, so number 4 is going to be relevant. We also need to look for Q1 being something, and that's stated by number 15. So 4 and 15 together explains number 16. And then we have number 17, which is that's our D1. So we're looking for the D1 definition. So I know what I'm looking for before I scan the statements. Okay. So the idea is you probably want to study, or you probably want to have studied enough that you can recognize just by looking at number 17 and tell that, oh, that's D1. And then you look for things that are related to D1 instead of reading number 17 first, and then you go back and try to recognize from the expression itself. So now we know it has to do with D1. So 3 is the definition of the D1. And now we have to say, okay, do we know anything about D1 at this point? The answer is no, we do not. All right, so number 3 may not be helpful in this case. So now the other way to look at this is, do we know Q1 and T1 at the same time? And the answer is yes, we do. Number 12 tells us what is T1. Number 15 tells us what is Q1. So between those two, we also can come to the conclusion that the exclusive OR is a 1. And nope, I take it back. Q1, T1, Q1, and then T1. Okay, that is correct. Okay, that's all good. Then we move on to number 18. Number 18 is the conclusion that D1 equals to 0. So that is a combination of number 17 that we just kind of concluded earlier, and also, how Q1 or D1 is defined, which is up here. That's number 3. And then we get to number 19. That looks like the exclusive or between x1, y1 to me. So once again, I can tell because I know the pattern. Okay, I know this pattern is the exclusive or between x1, y1. Okay, so I'm now looking at, okay, what is the exclusive or between x1, y1? Oh, it's just number 16. There we go. So number 16 directly explains number 19 without anything else. And then we move on to 20. So 20 is needed for we need two things. Number 19 is needed because that's where we can say, okay, the or between those two things need to be a 1. And now we need to look at, mm, now we have to say, okay, why can we be sure that this side is not a 1? Okay, that's hmm? 13. Oh, okay, very good. So 13 rules out the left-hand side being a 1 because we know that is a 0. So now between those two, we make a conclusion that the right-hand side of the OR has to be a 1. And with that, 21 is just because of 20, and 22 is also just because of 20. So that would be the answer for question number 1, of this particular version of question number 1. I don't know exactly how many versions there are, but I know there are a lot of different versions. So are we good with this one? All right. Are we seeing how this particular version of the test really is about the same as the practice exam? Because I think it's really important to recognize the similarity between the practice exam and this particular exam, because I mean that's a skill set that is actually needed at work. Okay, is to recognize similarities. All right, so we're moving on to Q2. So Q2 and Q3 are basically counterparts of each other. They are basically asking about the same thing, except they're not exactly the same. So we'll look at Q2 and look at part 1 first. So part 1 says, use the function vs applied to a bit pattern P. Explain and derive the bit pattern P that minimizes the value of the following expression or formula. Show your steps and reasoning. So when you read the question, it specifically asks to use the function vs, which means anyone who's bypassing that and just say, oh, the range or based on, the minimum value is just, negative 2 to the power of w minus 1. And because w is 6 and therefore it is negative 31, they definitely will not be getting all the points because the question specifically asks to link the explanation to the function vs. Okay, so the correct answer in this case is to use the definition first. So you basically you just boil it down to VSP6 in this case, and you have to expand it. Okay, you basically expand it to become P0 times 1 plus P1 times 2 plus P2 times 4. Now, I cannot do subscript here, so the P something is basically a subscript, and then P3 times 8 plus P4 times 16. Now, how detailed you want to go is up to you, and there are many other ways to express exactly the same thing that I will still go like, yeah, you can get full points because of that. So this is just one way to do it. Okay, this is the more mathematical description of a possible answer, but there are other types of answers too. But the point is, I need to know that you know how the formula expands. Okay, so that means and this is the crucial part. Okay, I'm missing something here. 1, 2, 4, 8, 16, and then this one is subtraction. There we go. P5 times 32. So this is the crucial part. Okay, because P5, okay, which is the most significant bit, is going to be subtracted. Okay, the product between P5 and 2 to the power of 5 is going to be subtracted. So that means, in this case, to minimize the sum, all the non-negative terms should be zeros. Okay, so that explains why P0 to P4 should be zeros. And then the only one that specifies the negative term should be a 1, and therefore P5 equals to 1. And that leads to the actual solution. And as a result, P equals to 1 followed by 5 zeros, 1, 2, 3, 4, 5 in base 2. So that would be the kind of answer that I'm expecting. It doesn't have to be exactly like this. Okay, you don't have to exactly use these words. You can list out all the powers of 2, but the 32 will have to be a negation or an arithmetic negation. You just say, okay, cross out these because they are not contributing to anything that's negative. Circle the one that contributes to the negative, and I will still count that as correct because I just need to know that you know how to expand VS. Okay, are we good so far with this one? Okay. All right. So we move on to part two. So part two is kind of the same thing. So I'm going to borrow the template from part one because the only difference is instead of using P, I'm using another bit pattern or another bit pattern name, which in this case is M for maximum, I guess. So M is here, and then we just substitute everywhere to be M, right? So we go. And once again, you don't have to use this format, but I need to know that you know how to expand um, the function. Okay, that's the key. Okay. All right. So once we have done this, then we can say to maximize the sum, m0 to m4 should be ones, m5 should be a 0. So therefore, m equals to 0, 1, 2, 3, 4, 5 in base 2. Is that okay so far? Now, note that the question never asked about what exactly is the value of VSPW or VSMW. It never asked for negative 32 or positive 31. It just asked about what bit patterns will minimize or maximize the value interpreted. Now, does that mean that if you mentioned, oh, by the way, this is interpreted as 31, I'm not going to take any points off, okay? But that itself is not a part of what I'm asking. Is that okay? All right. All right. So that's part one and two. Now we go to part three. So part three is about can you give me a um, bitwise subtraction with all the rows. Okay, so this is basically asking, do you know how multi-digit subtraction works? In this case, in base 2. So now we just go like 1 1 0 0 0 0 minus 0 1 0 1 1 0. And you don't have to specify base 2. It can be understood in this case. Okay, so minus that. So I'm expecting people to use the template that is already provided, which means you just fill in the gaps here. But if you want to kind of make your own, that's perfectly okay as well. All right, so I'm just going to do the bitwise operation method. This is a 1, this is a 0, 0, 1, 1, 0. Because what I'm doing here is I'm just looking at the exclusive OR between the X and the Y. And now I look this bit here, that's a borrow of 0. This has a borrow of 1, borrow of 1. This one has a borrow of 1. This one also has a borrow of 1. And this one has a borrow of 0. All right, so are we good with this row? Are we good with the T row, how I figure out each one of those zeros or ones? Yes? Okay, so the key here is I intentionally make sure that two of the borrows would be coming from the x minus the y, and then two of those would also be coming from the q minus the t. So that is intentional, even though your version will not have exactly the same bit pattern here, it will still be exercising the same kind of scenarios. All right? All right, so now we just have to get to the difference. So once again, the difference is really just the exclusive OR between the Q and the T. So now we have 0, 1, 1, 0, 1, 0. Okay, so that's basically the entire subtraction, and that's what I'm expecting part 3 to contain in this case. Do we have any questions about the answer to part 3? No questions? There's no explanation required here. Okay, the question did not ask about any explanation, but things have to line up correctly, and I will be evaluating the answer based on the consistency with the correct answers. All right, so we have part 4. Okay, so we move on to part 4. So part 4 is asking, given the outcome of the subtraction, what is VSDW? So I think it would be helpful if I label the rows, okay? Because in the answer space they are already labeled, but in my key here they are not. So X, Y, Q, T, and then finally the D. All right, so for part 4, we are basically saying VSDW, or D6, because we know W is 6 in this case, is going to how okay, so read the question carefully. Show how you use the definition of the function to come up with the answer. So in this case, once again, you have several ways to do it. You can do it like this, okay? If you don't like, making things, too formal because it takes too much time to write, you can always just kind of list out all the powers of 2, except the 32 is a negative 32. And then you just go like, oh, okay, we have 0 of this, 1 of this, 0 of this, 1 of this, 1 of this, and a 0 of that. So now you can just go like, oh, okay, when you add up all the ones, all the powers of 2 that has a 1 corresponding to it, that would be 2 plus 8 plus 16, and that is 26? No, yeah, 26. There we go. So that would be a perfectly acceptable answer for part 4. Are we good so far? All right. So then we move on to number 5. So number 5, or part 5, says compute the overflow flag. Start with the definition of the overflow flag as a Boolean expression. So that is very, very explicit. Okay. So you can use OV, okay, which is what I sometimes use. You can use lowercase o, you can use uppercase O, you can spell out the entire thing with a flag in it. Okay, so these are all acceptable. I just need to know that whatever follows is the equation that specifies the overflow flag. So the overflow flag is basically the most significant. It has to do with the most significant bits. Um, so we'll go ahead and take a look at that. So it is the negation of x5 in this case, because x5 is the most significant bit of x, and then it is ended with y5, and that is also ended with d5. And then we have an OR of x5 and the negation of y5 and the negation of, oops, sorry about that, d5. Okay, so what if somebody completely forgot about the overflow flag and go like, oh my God, I forgot. Okay, what is it? What do you think that person could have done or should have done or probably did? Exactly. Copy from the first problem, because the first problem actually tell you all that too. So the first problem, okay, let me show you what I mean by that. Okay, I think most of you know that already, but I'm just going to show anyway. Because the first problem already spelled out what is the overflow flag. So, even if you forget, it's okay. Just look at question number one and go like, okay, we got it. All right. So given that is how, this particular overflow flag is specified. Now we just put in those values from the earlier calculation. So x has a sign of 1, y has a sign of 0, d also has a sign of 0. So that means we have not 1 and 0 and 0, or 1 and not 0 and not 0. So the answer is this is a 0 or a 1. So the answer is there is an overflow of 1. We okay with this? Okay. And number 6, compute the L flag. Start with the definition. Once again, you can look up, in the previous one. So the L flag is the overflow flag. Overflow flag. I'm spelling it out just to be consistent. And then we have exclusive OR. I can't really use the circle with a plus inside, when I'm using just a plain text editor, but that's exclusive OR with the sign flag of the difference. So in this case, that would be D5. So once again, the template of the L flag can also be found in question number 1. Okay, so in case people forget about, oh, I don't remember what the L flag is, you can look up question number 1. So now we just substitute all the things here. This is one exclusive OR with D5, and I cannot remember what D5 was anymore, so I have to look it up. So D5 is a 0 in this case. So that would be a 0, and that is a 1. Okay, so the overflow is the L flag is a 1. And let me see if I missed anything. Substitute, show your steps. Okay, I think I did everything that the question was asking for. All right. Any questions about number 2? Do we still want to do number 3 because it's really about the same? So the ordering that you might encounter may be different. So some people get number 2 for the signed one. Some people get number 2 for the unsigned ones. Some people get the 8-bit version for the signed one. Some people get the 6-bit version for the signed one, and then get the other one for the other one. So I kind of, yeah, how do you call it? Mm, I created a lot of permutations. All right. So do we still want to go to number 3, or do you guys go like, okay, we get it. We get it. Okay. All right. So we go straight to number 4. So Q4. All right. So question number 4 is a base 6 subtraction. Okay. So the key here is it is a subtraction, not an addition. All right, so question number 1, or part 1, is asking what is the decimal representation of the y row. The y row in this case is 255. So 255 in base 6 is 2 times 36 plus 2 times 6 plus 5. Oops, there's a 5 here. There we go. 255. All right. So you can spell it out, like, using powers of 6, but if you just tell me 36, 6, and 1 are the things that you multiply each digit to, that's okay. Okay, I don't, you know, I don't have a problem with that. So now we just do the actual calculation, which is 72, 30, and a 5. And that will add up to 108, I think. Is that okay? Or did I do the math wrong? Yep, 7. Yep. All right. So that's part one. Part two is basically just filling in, all of those missing digits. So we'll go ahead and recreate, the scenario. We have unknown, 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 and then we have subtraction of 255. Oops, like that. So I'm just replicating the template that you guys got. And then we have 302 for Q, and another subtraction here. And then we also have unknowns over here. All right, so let's go back and figure out the unknowns. So we are looking for a value such that if you subtract 5 from that particular value, the single digit sum is going to be a 2. So in this case, I did not even bother to ask you guys what is the R function or how it should be defined, so that you probably need to look it up, okay, in your notes, or just kind of go by your understanding of the R function. In the subtraction, the R function is basically x, whatever this digit is, the one that's highlighted, plus the base, which is a 6, minus the 5, and then you take the mod of it, and that has to be a 2. Okay, so let me spell that out. Okay, so the equation that we're trying to solve is whatever x0 is, if you add a 6 to it, and then you subtract a 5 from it, and you take this entire thing, and then you mod it with a 6, which is the base, that should be 2. Okay, we're trying to solve for x0 in this case. So you look at this and go like, what can x0 possibly be? For people who absolutely hate algebra, okay, this is still solvable quite easily. Why? Because you just have to think about what kind of digits can x0 be. Let's see. 0, 1, 2, 3, 4, 5. Oh, so that means I can just exhaustively test those 6 values, see which one gives me the result that I want, and I don't have to practice any algebra whatsoever. Is that okay? You can brute force this, okay? So to brute force this, okay, I'm just going to practice what I said. Let's say x0 is a 0. 0 plus 6 is a 6. 6 minus 1 is a 1. 1 mod 6 is a 1. Nope, that's not what I want. So for people who don't recognize, oh, okay, so that means the next one has to be the answer, we'll just go ahead and actually try that out, right? So let's say x0 is a 1. 1 plus 6 is a 7. 7 minus 5 is a 2. 2 mod 6 is a 2. Got it. Is that okay? Okay, let me put it in first. So we'll just say that, okay, when x0 is a 1, it solves the problem. Okay, okay. So we just say, oh, okay, this is a 1. Do we have any questions about this? Nope. Okay. So 1 minus 5 has a borrow because 1 is less than 5. I don't even care what base we're dealing with. There's a borrow here. There's a 0 here, because I put a 0 here as well. All right, so now the next question, oh, this one is easy. What minus 5 ends up with a 0? That's just 5 itself. What minus 2 is a 3? That's also 5 because 5 in base 6, 5 does exist in base 6 as a digit, and 5 minus 2 is exactly 3, so that one is fairly easy to figure out. So now you look at the borrow flag here, okay? 5 minus 5 is not going to have a borrow, but 0 minus 1 does have a borrow. So we have to stick a borrow here. And then the borrow over here is going to be a 0 because 5 minus 2 does not have a borrow. 3 minus 1 also does not have a borrow. So if neither has a borrow, then the overall borrow from the next digit is going to be a 0. And now we just have to work out the last row. 2 minus 0, single digit wise, is a 2. That's an easy one. 3 minus 1 is also a 2. That's also an easy one. 0 minus 1 as a single digit, well, let's plug that in, right? So you have 0 plus 6 minus 5, and then the whole thing mod 6. That is a 1. Wait, that doesn't make sense to me. Oh, because I did not put in the correct digits. That was my bad. Okay, I was just copy and pasting, which you probably would not make the same mistake because you're not going to copy and paste. All your answers are going to be handwritten. All right, so we just look at this. 0 plus 6 is a 6. 6 minus 1 is a 5. 5 mod 6 is also a 5. So that means a 5 goes here. So now we have all the digits we figure out, which is number 2. That carries the majority of the points of this particular question, but there's one little thing left, which is part 3. Part 3 is asking what is the decimal representation of the value represented by the D row. So the D row is the 252. So in this case, we just say, okay, 2 times 36 plus 5 times 6 plus 2 times 1 is 72 plus 30 plus 2, and that would be 104, I think. Yep. All right. So do we have any questions about all 4 questions and all the parts? No questions? All right. So with this, I call this kind of class or the class right after the exam where I review, the questions or review the answers. I call this the salt rubbing session. So you go like, why would you do that? This is painful. Because if I don't do that, the wound is unattended to, and it can, have problems. Okay, so this stings a little bit. So the question is, what are you getting out of this particular session? In other words, you compare this to the way you answer the question, and then you ask, okay, so did I answer the questions in an efficient manner? Okay, so it is possible that somebody studied and studied and studied and yet did not answer the question with the efficiency that I did. Now, it is not a fair comparison, I know, okay, because I've been teaching this class for a long time, and this is also my questions to begin with. But still, okay, the question is, did I make all the connections that were needed in order to answer the questions with the efficiency or without the efficiency, or did I miss something? Okay, so that's a self-diagnostics for people, for each individual to go through. And in that process, okay, hopefully it will help you refine the way you study, at least for this class, and refine the way that you take notes for this class, and the way to, and refine the way that you try to absorb the material for this class. Okay, I'll be more than happy if people say, okay, but I think, you can change the way you teach the class in a certain way to help me. Let me know. Okay, you'll come to my office hour, or you can tell me in the class. Okay, I don't have a problem with that either. Okay, so the idea is go through the process. Okay, figure out how you can improve this in the next exam. Okay, the first exam is 20% of your entire grade, and some people go like, oh man, if I totally bomb this test, it's gonna, I don't have a chance to get a B anymore. I'm failing the class already. Well, that is not the case. Okay, read the syllabus and you will figure out that, oh, I can still pretty much pass the class, likely to even get a B, and remotely even to get an A. So you guys would go like, no, that is not possible. How can someone possibly get an A after bombing out one exam, right? One entire exam. So I'm going to show you the math. So the math is, so assuming most people are doing the labs okay. So let's say out of the labs, most people are getting, I'm hoping people are getting about 18% or so at least, okay, which is 90% of all the available points. At this point, okay, because everything is set up, so that you can resubmit as many times as you want, okay, except for the file submission and stuff like that. But even for the file submission, other than the PD, NC, year one, I gave you the test circuits so that you can actually test everything before you turn in to make sure they are all good, right? So that means the chances of missing too many points in the lab is pretty low. So in exam one, let's just take a fairly extreme case of somebody just got a 5% out of the 20. Okay, so that means it's actually a 20% out of the test itself, but contributing only 5% to the final grade. So now we've tried to figure out, okay, what about exam two and what about the final exam? How can this person possibly get an A in this class? So these two together is adding up to 23%. So tell me what is the percentage that you need to get an A in this class? Okay, just because of that answer, I'm gonna take points off of your next exam because you didn't read the syllabus. The single one most important thing to read as the semester starts is the syllabus. Okay, 87.5%. Okay, so that means, okay, I need to fill this gap to 87.5%. So you do a subtraction, right? Yeah, so I'm gonna do my own subtraction here. It would be a 64.5%. So the delta is 64.5%. And somebody's going to say, but Tech, this means it's not possible. Why is it not possible? Because the second exam is only 20%. The final exam is only 40%. So that means even if I get 100% from each one, I can only add up to 60%. I'm still 4.5% short to get an A out of this class. Well, yes, but there's an unspoken thing that I usually do, which is quote unquote rebalancing what I consider to be a 100% of this class. Okay, now this class is big enough, or there are enough people in this class, I can use this approach. So normally what I do is I take the 90th percentile score in a test. Okay, so let's pause. Okay, what does it mean when I say the 90th percentile score? Can someone help me explain what that means in an exam? So let's say there are 30 people. So you're correct. So the third highest score of this class is approximately the 90th percentile score. Is that okay? All right. So let's just assume, for the sake of for this argument here, for the final exam. Okay. So let's say for the final exam, um, the top three scores in this class, the raw score, which means that's exactly the number of points they're getting. The top one is 86%. The second one is 82%, and the third place is at the 75%. Okay, that makes things easier to calculate. Okay, so let's say that is the case. So what that means is I'm depending on the actual distribution. Okay, so I'm not saying this is always what I would do, but this is normally what I would do. Is I would look at this and go like, okay, let's turn that into a new 100%. So if I do that, okay, that means this person who actually got 75% to begin with will now be the new 100%. And then the rest of the class is scaled accordingly, which in this case is easy to compute because it's just 4 times. It's basically multiplying everything by 100% divided by 75, which is times 4 and then divided by 3. Okay. So that means the person who got 86% to begin with, the 86%, okay, would be multiplied by 100% and then divided by 75%. So that would be, okay, someone can do this more quickly than I do. Okay, so it's times 4 divided by 3. So 86 times 4 is 344. And then you divide it by 3. So 344 divided by 3. There's a 1 here, there's a 1 here, and then how many? There's a 14. 14 divided by 3 is at least a 4. So that means, the top score of the class, the person who scored the highest score, will now have 114% of the 40%. Okay, and the same thing is going to happen to the second exam too. So that means somebody who got a 5% out of exam one can potentially still ace this class. Well, I shouldn't say ace the class, can potentially still get a letter grade of A. Is that okay? Does everybody kind of see the math? All right. Yep. I do it to every single test. Unless I see a pattern where people are conspiring. It's like, okay, we'll all agree that everybody is going to put in the minimum effort to get 1 point. Okay. So if I see something too obvious, then I would not use that approach, right? But generally speaking, for normal class, I typically use that approach. And sometimes I would even move further down if there's an uneven distribution. There was one class last 2 semesters ago where I had like 6 people who are usually sitting in the back. They always take classes together and they do not copy from each other because they're too competitive to do anything like that. So after class, they're just kind of comparing their own grade. It's like, ha, you suck, man. You know, so they would never, ever, okay, try to copy off of each other, and they are all overachievers. So for that class, we have 6 people who are sitting all the way to the top. And so if I only use the third highest score, I wouldn't be touching, the intended target. So I would make adjustments based on the actual distribution. But typically, I would use the third highest score or the 90th percentile. It doesn't work as well when I only have like 11 students, which is my Monday, Wednesday class, because in that case, the distribution can be off by a lot if I just move by one person, on that scale. All right. So is that okay? Does everybody kind of get an idea of this is really quote unquote just the first exam? Okay. So don't get too discouraged if you did not do as well as you thought you would do. Okay. So the idea is learn from this. Okay. And so the next time you'll be more prepared. You know how I would ask questions and what I really test on, okay, which is your reasoning. Do you know where to find the equations, the formulae, and so on and so forth. All right. Any questions about the exam before we move on to the next topic? No questions? All right. So if there are no questions, I'm still recording. I just want to double check. So the next topic is to kind of go back to what we talked about the other day, which is the SR latch. But we are done with the SR latch already. You guys did the PD, NC homework assignment or lab already, so we are pretty much done with that topic. Except that module actually has a lot more that we have to go over. All right. So we're going back to the memory device module. Okay, so we'll go ahead and open it on the side over here. So we are pretty much done with section 3. So we are moving on to section 4 now. So section 4 is called a D flip-flop, which is also known as a level sensitive D flip-flop. I'll explain that later. But the first thing I want to explain is what is this? This is not doesn't look like a circuit to me. It looks like object-oriented programming code. Well, that's exactly what it is. Okay, I'm using object-oriented code to describe a circuit. So in this case, when you see uppercase not, it is a class, and n is a variable of that class. In other words, n is an object of the class of not not. And then we have NAND2. N1 is a NAND2. N2 is also a NAND2, which means it's a 2-input NAND gate. SR is a SR latch. Okay, so I'm using SR latch itself as a class. which is equivalent to using SR latch as a circuit, as a sub-circuit in Logisim. D and EN are both input pins. Q and NQ are both output pins. So that means this portion of the code is telling you what components we have in the circuit and the names of those components. Are we doing okay so far with that concept? Okay, it is equivalent to in Logisim. I go to the left hand side, I take a NOT gate, slap it on the right hand side. I go back, look at the NAND gate, pick up one of click on that, and then click twice on the right hand side. So I have two components. Go back in, change the name of the components, and so on and so forth. Okay, so this is how we put components into the circuit. Then what about the rest of the code? What is this? This is how we drew wires from between the ports. So in this case, I'm creating a node. That node is interconnecting the pin port of D to the first input of N1 to the only input of N. So those three ports are now connected. It's the same thing as drawing the wires, okay, in Logisim, except in this case, everything is just logical. Are we doing okay so far? Okay. I will show you the equivalent circuit in just a moment, okay? So you will see the graphical one. So I use this method to create all the additional nodes, and this one is a little bit more complex than the SR latch, because in this case we have 7 nodes, and each one is connecting at least 2 ports together. Some of these connect 3 ports together. Do we have any questions about how to interpret the text representation of a circuit? Okay, no questions. Why are we doing this? Why don't we just use the Logisim diagram and so that everything is GUI and graphical and easy to understand? It builds critical thinking. That's one, okay. And also because when if there's a harder way to do something, tech will find it and make sure that we all use it. Yes, go ahead. Okay, you could do that with a GUI approach too, right? So the difference of doing this versus the GUI, graphical method is the same difference between using a GUI program to do text editing or to copy, even just to copy a file from one place to another place in the folder, as opposed to using the command line. The command line interface, okay, you guys know the command line interface, right? Okay, we introduced that concept already. So what is the difference? Okay, if I use the GUI method, I just have to drag and drop. Everything is very intuitive, easy to do. So why would I want to know how to do it on the command line? Efficiency. So, okay, so that's good. We're heading in the right direction. In what way is the command line improving efficiency? It is, you can do it much faster, okay, because you can just kind of cursor up and do it. But it also makes it possible to turn it into an algorithm, to do it programmatically. Okay. Okay. So imagine this. Okay. Imagine this. Okay. You have a folder with all the photographs that you took in the past year or so. All right. And by the sequence number of the photographs, you know that there's a certain range that you want to move to a particular subfolder because they're all related. So maybe it's an event, somebody's birthday, whatever, right? So if you do it by hand, then you'll be visually looking at the file name, okay? Drag, drop, drag, drop, drag, drop, drag, drop. So let's just say that it was a particularly memorable, event, and you took 216 pictures. Then you'll be doing this. I mean, I know you guys know how to select a block and stuff like that, but it's still, okay, you still have to do it visually, okay? But if you know how to do it in on the command line, you can just write a script. Or if you know how to use regular expressions on the command line, you can just specify, okay, this is the range of numbers of the image files. Copy every single one of these over here. Okay. So that's a very simplistic um, scenario that you can automate. Okay, what if it is a little bit more complex? Okay, what if it has to be a picture taken on this date, or, or a range of dates, and then you have a specific time frame of the day as the criteria. So now you can't really do it visually and just do a block select anymore because it depends on the day, also the time. But if you use a script to do it, you can quite easily filter, okay, everything based on the range of date, based on the range of time, plus whatever condition you want to attach to the whole thing. You can do it programmatically. Is that making any sense? Okay. So this is the same way. Okay. There are certain types of circuits, that are very tedious. Okay. They're not difficult per se, but they're very tedious. So if you were to do it by hand, you'll be doing it like, everything is tedious. But if you write, you can actually write code to create a circuit that has repeating patterns. You can use loops. You can use conditional statements. Everything that you learned in CISP 360, you can apply that, except you're not doing C out to generate a text file anymore. You are creating a circuit using logic. So you're not doing C out. You are basically building a circuit using these particular similar kind of statements. So that means you can build very complex circuits with a huge number of components. As long as you know the structure of how everything is supposed to connect, you convert that structure into code and then let the computer handle the rest, which are the details. That is why this approach is better when you have really complicated circuits. We good so far? Yep. Yes, but there are people who can help you to deal with all the low-level details. So VHDL is oh, that's not the one that I want. Language versus Verilog. There we go. These are the two industry standards for using text to specify circuits. Um, One is called VHDL, the other one is called Verilog. Verilog was never intended for this purpose. It was basically, industry people go like, hey, we can use this language to specify circuits. Let's do that. Okay. VHDL, on the other hand, was purpose built or purpose engineered to specify, hardware because the name itself implies it. Because VHDL stands for um, Virtual Hardware Description Language. I'm not 100% sure about the V, but I'm really sure about the hardware description language. So I mean, people actually made up entire languages to do this. Okay. All right. So this is just explaining the reason why I converted from the graphical representation to the text representation. In the next exam, there will be a question like this. Okay, I will give you a description of the circuit, and you have to be able to track down, how the signals propagate using the PDNC, tables. So there will be a question. This is a promise. Okay, so it sounds like it is a promise, but it is also me helping you to get ready for exam two because you know what it will have already. So that means when we talk about these topics, you might want to jot down some notes. Make sure that you understand everything. All right. So with this circuit, it is already built because I actually built it in the other class. So let me see whether I can find it. Yep, found it. And yep. So I'm going to put it into your view. There we go. That's not it. So level sensitivity flip-flop is this one. So this is the corresponding circuit to what the text was describing. So let me see if I can display both, side by side, just so that we can see, oh, okay, so that's the text version of this, and that's the graphical circuit representation of that. So I'm gonna use the usual approach. Okay, this is the lazy but effective approach to just take a certain portion of one page and overlay it to in this case, the circuit. Okay, so let's take a look at the comparison. The left-hand side or Logisim is displaying the actual circuit, and then the screenshot is displaying the text version of the same thing. All right, so we have a NOT gate, and here it is a negation. We have N1, N2, both being two input NAND gates. So here's one, here's the other one. We have SR latch as a regular SR latch. This is the SR latch, which I actually made out of NAND gates. So this is something that I actually made, but I use it as a component inside a regular D flip-flop. So there's that. And I probably want to save the file before I lose it. Let me save it to documents, CISP 310, D flip-flops.circ. There we go. All right. Let's take a look at the input pins. D and EN are input pins. Q and NQ are output pins. So those are all the components. And we're going to just take one node as an example. Okay, we'll take this one, the second one, this one here. So we can see how EN, which only has a single port here, is connected to the second input of N1, which is this one here, okay, like that. But they are also connected to the first input of N2, which is this one over here. So that makes a single node. If you count the wires, it's like, oh, so how many wires are we going to count as? It doesn't really matter. It is one single node. On the circuit board, it is one contiguous piece of copper connecting all of those ports. Okay. Now, Logisim also gives you some kind of nifty little tool. If you're in the poking tool mode, you can actually click on a wire, a node, and it will highlight the entire node, not just the wire itself, but the entire node. So that really helps to kind of highlight, okay, where is EN connected to? Oh, we can now see clearly that it connects to the second input of N1 and the first input of N2. Are we doing okay so far? Are there any questions about how the Logisim circuit is corresponding to the text description of exactly the same circuit? We good? All right, cool. So now the question is, what does it do? Okay, what is the whole purpose of this circuit? Okay, why do we need it? All right, so can I hide this one or close this window? Okay, all right, so let's close this. So now the question is, why do we need this circuit? What does it do? D stands for data. Okay, in other words, this is the information that we want to store. Okay, and the storage, quote unquote, is the SR latch here. This SR latch is responsible to store one single bit. Okay, so it's constantly asking, am I supposed to store a 0 or 1? Okay, and whatever it's storing is reflected in the output pin Q, and Q for the most part is useless. Okay, it's just a negation of Q. So now, how do we change it? Okay, you can see how, attack, this is not working because D is a 1 and the device is storing a 0. It's not working. Well, it's not like it is not working. It's because EN is a gate or it is an enable. EN stands for enable. So when the enable pin is a 0, the device is ignoring D. Okay, you can basically go to the D pin here and change it all day long. Nothing happens because EN is a 0. You can think of EN as a kind of on-off switch. Okay, when it is off, the device ignores the input, but it will still maintain its memory state. So if you want the output to change, okay, you have to first enable the enable pin, okay? So once the enable pin is 1, then the device will mirror whatever the D pin is, it will mirror that to the Q pin and remember that. So now we can see, oh, okay, so let's give it a try. Aha, okay, that works. Oh, that works too. So as long as EN is a 1, any change of the D pin will eventually be propagated to the SR latch so that the Q pin is going to be an exact copy of the D pin. Are we understanding that concept? So now when you get this, okay, the one thing that I want you guys to practice is to do the PDNC analysis. Okay, assume everything is unknown. Okay, and then you go like, okay, everything is unknown. I'm first going to turn both inputs to zeros. Okay, and then you turn the D pin from a 0 to a 1, and notice that the output pin Q is not going to do a single thing. And then you turn on the enable pin so it becomes a 1, and you can see how the Q pin is now reflected, by is now reflecting the D pin. But as long as the EM pin is a 1, if you turn the D pin back to a 0, you can see how the Q pin is also going to return to a 0. So the transitions that I have just made would be something that you can practice on, okay, using the PDNC analysis so that you understand, oh, okay, so how do we, you know, how do we figure out, what is going to change because of this change and so on and so forth. It gives you more practice opportunity. Yes, I'm not sure what you mean by that. So one thing you can do is you can make your own circuit and give it a try. That's that's why Logisim is great because I'm not 100% sure what you mean by when you told me the connection using words. So if I see it, I can probably understand it a little better. But if I cannot see it, it's hard for me to evaluate it or to comment on it. But getting back to practices, so I have told you about something that you can do to help you understand more about the circuit, one, and two, have a chance to practice your PDNC, okay? And you can do it in any sequence, right? Because the idea is your prediction of what the circuit is supposed to do should match the logic sim results here, okay? You don't have anything to turn in. I'm not going to grade anything, but in the process, if you run into any questions, you go like, hey, my circuit is working like this in Logisim, but my prediction is wrong. Okay, I'm not predicting exactly the same thing. Come to my office hour. I'll be more than happy to take a look and find out where the discrepancy is. We good so far? All right. So now we go back to the notes and then we move on to another circuit. So this one is called edge sensitive D flip flop, okay, which is one of many names that it can take on. So let's go back to the circuit here because I also made that circuit over here. So this is what we call a edge sensitive D flip flop. Now, when you do the simulation in Logisim, it is also helpful to turn off simulation, reset the simulation so that everything starts with an unknown state to begin with. Okay, it's always helpful to do that, to reset everything first. So when you first start the whole thing, okay, that's let me reset it now. Okay, this is normal. Okay, so you ask, why is SR latch C outputting an error? Well, it's not really an error per se. It is just saying that we have no idea whether that is a 0 or 1 because you can see how the two inputs of SR latch C, they're both ones. So can someone look up the truth table of an SR latch and tell me what does it mean when both inputs of an SR latch are ones? I believe in my notes, I use NC to comment those, the output Q and the NQ. So what does NC mean in that case? No change. Very good. Okay, excellent. It means no change. No change from what it used to be, right? I just reset the entire circuit. So can someone tell me what is the quote unquote default value of the output of an SR latch is supposed to be? There's none. An SR latch does not have a default start value, and therefore it is coded in red because we don't know what it is. We just don't know. Okay? So this is perfectly normal. So in this case, instead of EN, we have CLK. CLK is clock. So that mean what that means is I can change D all day long, nothing happens to the output. Okay? So let's just say that I want to remember a zero. The the update in this case is not level sensitive, it is called edge sensitive. What that means is it will update the output only at the instant of time when clock is transitioning from a 0 to a 1. Okay? So from the software people's perspective, it will take like 0 nanosecond because we think everything is idealized, right? But in real world, it does take some time. Okay, everything has a propagational delay, blah blah blah, and so on. So ideally speaking, the clock has to the transition is not exactly instantaneous. It actually takes a little bit of time. So let's go ahead and do this. Okay, look at the screen. Okay, we have D being a 0. The current output is unknown. So the moment I click on the clock pin so that it goes from 0 to 1, look, click, the output becomes the 0. Okay, but that's it. Okay, it's a one-shot deal. So until we have another transition from a 0 to a 1 on the clock pin, the output stays put. It does not change at all. So that means I can now go to the D pin and play with it. Absolutely nothing happens. Okay. I can turn the clock pin back to a 0. This is a falling edge. It is not sensitive to a falling edge. So that doesn't do a single thing either. And I can now go back into the D pin and play with it again, and also nothing happens. Because the update occurs only when the clock pin transitions from a 0 to a 1. Is that okay? So in real life, there are things like that too. Okay, if you play any kind of instrument, musical instrument, you probably know what is a metronome. Yes? Okay. So now whether you actually use it and follow it is a whole different thing. I know because I used to play the piano, and my piano teacher says, Jack, you have to use the metronome because your tempo is all over the place. Yeah, so even if you have one, whether you actually use it or not is a different thing. But when the metronome makes that click, that is the timing, right? It is telling you this is the beat, 1, 2, 3, 4, 1, 2, 3, 4, and so on. So in this case, it is clock, the clock pin serves exactly the same purpose. It controls the timing of the update. Is that okay so far? All right. So now we move on to another one, okay? And this one I did not actually make a circuit of, but we can talk about it in here. So the next circuit looks like this, okay? It is another level of, complexity. This one is called the level sensitive and edge sensitive D flip-flop because it has both. So it has got a clock, it has an enable, it has the data, it also has the output of Q. Now this one I did not make it in my own Logisim, which does not say that you cannot do the same. Okay, so I highly encourage you guys to actually make it and play with it. Okay, so with this one, in order for the output Q to be a mirror of the data input pin, two things must happen. It has to satisfy two requirements. First of all, the enable pin has to be a 1. Second of all, the clock pin has to be transitioning from a 0 to a 1. So you're asking, why do we need both? Okay, because they control different things. The enable pin is allowing multiple D flip-flops connected to the same data line. And using the enable, you can say who should be paying attention. Okay, because if the enable pin is a 0, the D flip-flop is not even paying attention. It's not even paying attention to the clock pin. Okay, so once a device is enabled, which means, hey, I want you to pay attention, but don't update anything yet until I say so. So the clock pin is for controlling the timing. Are we good so far? So I'm not sure how many of you have watched like an orchestra with a conductor, right? So the conductor will be you're providing the basic tick, right? You're using the wind. That's the clock pin. The entire orchestra should be synchronized to the clock. Otherwise, you have an unpleasant experience at the concert, right? Okay, so that's one. But sometimes the conductor will look at a certain section of the orchestra. It's like you guys are being too loud. Okay, you simmer down. Okay, because certain instruments are just naturally louder than others, right? And then other times, the conductor will look at another section, usually the flute section, and go like this, because flutes are, basically intrinsically a quiet instrument. Okay, so that is the enable pin. Okay, the enable pin is saying you talking to me, and that's what the enable pin basically says. Here's a lot of instruments. Okay, is the conductor talking to me? That's the job of the enable pin. It allows the conductor to basically say, yes, I'm addressing you, this entire section of instruments, a little bit louder. Are we doing okay so far with that analogy? Has everybody been to a concert or at least watch a video with the orchestras playing? Okay, very good. Because otherwise, we're going to have a field trip. Yes. That's a good question. So I'm going to introduce, but it's not going to be in the test. I will introduce what we call a waveform diagram. Okay. So if you look at the data pin, okay, so let's say this is the data pin, this is the clock pin, and this is the enable pin. Okay. So let's just say the data pin is going to, so typically what they do is they use crossing like this. Okay. So we'll basically say that, okay, during this time, the data is correct, okay? And this is when I need the D flip-flop to remember something, okay? So typically what you want to do is to have the enable pin to turn on right about this time for almost the entire duration, okay? But the clock pin, on the other hand, would not make any transition until it is close to the center of when the data is valid. Now, when it drops back, it's not really a big thing. Okay, so most of the time you want it to drop back, after the data is gone. So, but it really doesn't matter because it only has to be on like for a really short amount of time. So is that making any sense? Yeah. Yeah, this is called a waveform diagram. So if you are going to become a computer engineer or an electronic engineer, you'll be reading a lot of these diagrams in data sheets. Absolutely. Yep. Yep. Okay. All right. So this one is a little bit more complex to simulate using just a table, but it's doable. Okay. So for those of you who are going like, okay, I want to test whether I can model this kind of stuff. It's a little bit more complex, but I want to see whether I can do it. Go ahead. Okay, but it's not going to be super fun. Okay, because it really is just a combination of the previous two. So of all of these, I would say the clocked or the edge sensitive D flip flop is the most interesting one because it can, because one of the components can have a transient state. So we have talked about the steady state, right? The steady state means you can do all the NCPD cycles all you want, nothing is going to change. Okay, that's the steady state. We talked about oscillation, right? Which is, oh, okay, this pattern of going from 0 to 1, going back to 0, or we have some kind of a cyclic thing, and the circuit does not settle on a particular state. So that's a oscillation. But as it turns out, there's a third one. It's called a transient state. So a transient state is a temporary change of a state between steady states. So eventually you do arrive to a steady state, but between the steady states, there is a state change that goes back and forth. It's called a transient state. So the clock, excuse me, I take it back. So the edge sensitive D flip flop actually has a transient state. So it is an interesting circuit to simulate just so that you can see the transient state. So some people may go like, but I don't want to go through all that trouble in the spreadsheet. I can just go to LogicSim and do it this way. Well, the answer is nope, you cannot. Even though the steady states in LogicSim will be 100% correct, it does not let you see the transient states. So the transient states are only visible when you are doing the tracking or the tracing in a table and do it by hand, alternating between the PD and the NC cycles. So that's something that you might want to do is to simulate this particular circuit using paper, and just kind of go through the cycles that we talked about, when we update, with when clock transition from a 0 to 1, and then just kind of play with the data pin, flip it back and forth, and then you can see, how it is or how it is not affecting the Q pin. Are we good so far? In terms of your recommended activities that you can do in order to have a better understanding and also to have more practice with the things that we have done already. All right. So with that said, um, we'll move on to the next one. Since I don't have a lab for you today, we have not talked about enough topics for today's lab. So what I will do is I'm going to extend the lecture by about half an hour into the lab time, and then we'll end the lab time earlier today. Is that okay? Because I don't want to waste our time either, but I also don't. I understand that I cannot just extend the lecture to be twice as long, because attention span is can be an issue, right? So no, I actually don't understand, but people have told me about the issue of attention span. When I took assembly language programming, okay, this is my way of kind of giving you guys a short break. When I took assembly language programming from San Francisco State University, that was 1986. You guys go like, wow, my parents are not that old. You would be probably correct. So when I took that class, it was a 1 day per week kind of class, but it wasn't hybrid. It is face to face 1 day per week. So the lecture was 3 hours long, and it was an evening class. The class started at 7 p.m. and it ended at about 10 p.m. Um, the lecturer or my professor was a lecturer at UC Berkeley, so at Berkeley has always kind of stretched that class to talk about virtual memory and other things that are really way too advanced for a class like this. So when the class started, we had 60 students, which is quite a lot, quite a lot. Okay, it filled up a small auditorium. By the time the semester ended, we had 12 students left. 20% of the class, kind of went all the way to the end. Anyway, but it was a fun class. I really enjoyed it. And so I was talking about this only because, when I said I understand, the attention span thing, I actually do not because I don't have that problem. But I understand that some people may not be able to kind of sustain the attention span, and it's okay. Okay, people are built differently, and it's perfectly fine. All right. So getting back to the material. So now we move on to something that's even more complicated. It's this one here. No, this we just talked about that one. We're now talking about this one. So when you compare this one with the one before, you will see that it's almost the same. What is the big change here? So once again, I'm going to use this tool to kind of show you the differences side by side. Not a perfect clip, but it's going to be fine. So always on top. There we go. Scroll down. Okay, so now we compare these two circuits. And you can probably see that, oh, they're about the same. This one is SR1, this one is SR1, this one is A1, this one is A1, and so on. So the only difference really are these two components in between. Okay, this is O1 for OR gate, this is A3 for an AND gate. So now you go like, okay, this wire used to go directly to the S input of the SRC, and now it's going through one side of the OR gate before it goes to the S pin of the SRC. This output here used to connect directly to the R pin, like here, but now it's going through the AND gate before it gets to the R pin, and both of these gates have some way to connect to a new input pin that we call reset. So what's going on here? So now the question is, um, if the reset pin is a 0, what is it going to do? When the reset pin is a 1, what is it going to do? So we'll start with 1. Okay, what happens when the reset pin is a 1? So now you look at this and go like, okay, this is now a 1, and this is now a 1. So the question now is, if one of the inputs of an AND gate is a 1, what is the AND gate actually doing? Whatever the other one is the output. Let me say that one more time. Okay, I'll say that one more time. If one input of an AND gate is a 1, then whatever the other input is really just a pass through to the output, which in the equation sense is basically saying if you have, true and some Boolean value y, okay, that is guaranteed to be the same as just y itself. Is that okay? Does that make sense to you? And some people go like, well, Tag, whatever you say seems to make sense to me. Okay, no, 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 no. I want you to be really convinced that it makes sense. How do we do that? Oh, I know how to do it. I'm just gonna pop up, ChatGPT and ask ChatGPT why, it is like that. In fact, I'm gonna take a picture and just have ChatGPT figure that out by itself. Nope, you don't need to do that. We have talked about something that starts with a T that can be used for this. What is it? The truth table, exactly. So how do we use a truth table for this purpose? I'm telling you all of this stuff here because I want you to have all the tools so that you can basically verify things to your best ability, in at least in this class. Okay. So now we look at the truth table. X can be a, X is one Boolean variable, Y is the other one. But the expression that I'm interested in is just one and one of them. Okay, let's say y. Okay, actually, let's do it this way. Okay, I think this is a better way to do it. There are two ways. There are several ways to do it, but this is probably the best way. So we have 0, 0, and then this is going to be 0. We have 0, 1. This is also going to be 0. We have 1, 1. This is going to, oops, 1, 0, sorry. 1, 0. This is going to be 0, 1, 1. And this is also going to be a 0. Okay, so the question now is, what about 1 and y? Okay, why, what is going to happen here? So that means we are only looking at these two rows. Does that make sense? Because, 1 is already true, and I made a mistake here. Sorry, this is my mistake. There we go. So we're only looking at these two rows over here. And you can see that on these two rows, as long as we know y, excuse me, as long as we know x is a 1 because it's a constant here, whatever y is the result of the conjunction. So therefore we know that, oh, okay, I see why they are the same. Is that okay? All right. So, okay, well, I'm gonna keep I will keep the truth table here. So now we go back to the circuit and then we look at the other one. Okay, so we now look at the other side, which is an OR gate here. So this OR gate is looking a little funky, okay, because hey, how come one of the input has a bubble? That bubble is a shorthand for negation. In other words, the second input of the OR gate is negated first before it reaches the OR gate itself. Okay, so now the question is, what is it going to do? So we are still talking about when reset pin is a 1, right? So the 1 goes all the way here. The 1 is now negated to a 0. So we are really looking at 0 or whatever the other input is. And what is the output in that case? Well, it is also going to be a it's also going to be a pass through, because if you have a zero on one of the input of the OR gate, then whatever the other input is going to be the actual output. Okay, so we can see that also in the truth table. So let's go ahead and use the truth table again. Once again, we have x, y. This time we have x or y, and then we have the same setup for 0, 0. This is a 0, 0, 1 is a 1, 1, 0 is also a 1, 1, 1 is also a 1. But in this case, we are looking at x or 1, right? X or 0, sorry. So we're looking at x or 0, and we're asking, what is that? So this time it's a little bit harder for me to look at both at the same time because my editor only allows me to select one block at a time. So this is one, and this is the other one, because on both of these rows, y has a value of 0. So we can see how x or 0 is the same thing as x. X or 0 is also just x. Are we seeing that? Okay. So in mathematics, conjunction is kind of like multiplication. You can say x times 1. Okay, what is x times 1? Whatever x is. When you look at disjunction, it's kind of like addition in algebra because you're adding 0. Okay, x plus 0. What is x plus 0? Whatever x is. So it's the identity of that operator. Okay, both of these are identities of the operator. So what this really means, okay, is if reset is a 1, it is as if these components did not even exist. It's just a pass-through, just like the other circuit, okay? So it's just like this circuit here. It is just a pass-through when reset is a 1. So now the question is, what if reset is a 0? So if reset is a 0, the AND gate is guaranteed to output a 0. Okay? If reset is a 0, the negation of the 0 becomes a 1, so the OR gate is also guaranteed to output a 1 in this case. In other words, by changing the reset pin to a 0, we are now guaranteeing the S pin is a 1, the R pin is a 0 for this final SR latch, independent to what everybody else has to say. Is that okay? So if you look at the truth table of the SR latch, if the S pin is a 1 and the R pin is a 0, what is it doing? Do we know what state it should end up as? We do. The Q is going to be a 0 and Q is going to be a 1. We know that for sure. It is deterministic. So that means, oh, okay, so that means when the reset pin is a 0, we are guaranteeing to reset the SRC latch so that the output Q is a 0. And that's why it is called a reset pin. Is that okay? So the reset pin is basically what we call an asynchronous mechanism to reset the state of a D flip-flop to 0, regardless of what the inputs have to say. The device can be not enabled and the clock is not even moving anything and the data is floating. It doesn't matter. It will change the final SR latch, which is SRC in this case, to output 0. Now we have a reset mechanism. Why do we need a reset mechanism? Hmm. Correct. But it also goes back to something I have demonstrated earlier in the class, even though it wasn't on a circuit like this complicated, but it was still a circuit that can demonstrate, what I want it to do. Okay, let's go back to this circuit here. This is the edge sensitive circuit. The other one would do the same thing, by the way. I go to simulate, I reset simulation. See how it's giving you an E here? Because we don't know what the state is. We know it can be a 0, it can be a 1. We don't know which one it is. So guess what happens when you power up your computer? It is the same thing. We don't know which way it is. Okay? So now when you start up the computer, Ideally speaking, you want the computer to start execution at location 0. But without knowing what the default state of all of these circuits are, it will start at a random location out of 2 to the power of 64 choices. So that means every time you turn on your computer, you have a chance of 1 in 2 to the power of 64 that it will start at the right location. So you turn it on, nope, turn it on, nope, turn it on, nope. And if you do it enough times, there's a chance that it will start at a certain location that you want. So the question is, do you want your computer to behave like that? Do you want your phone to behave like that? Do you want your fitness watch to behave like that? Probably not, right? It would not be good use of your time, or in this case, your life, because 2 to the power of 64 is a huge number, okay? It is a gigantic number, okay? So what do we want? We want to say, hey, computer, when you start, just start with location 0. That's all I want, right? This is the mechanism to make it happen, okay? So now the next question is, well, but when I power my computer, I don't have a reset to go along with the power button that I have to hold both at the same time, and then I release the reset button, then I release the power button. You never have to do that. Why? Because inside the computer, we have a circuitry called a watchdog circuit. Okay? The watchdog circuit has two primary functions. The first one is a reset or power up reset. So now the question is, when you power up your computer, how long do you think it will take the voltage to your processor to ramp up from 0 volts, which is ground, to the operating voltage of whatever your processor needs? How long would it take? It's more than milliseconds. It's more than single milliseconds. So it would typically be measured in hundreds of milliseconds. It's a fairly long time by the standard of the clock speed of a processor. Okay. So during that time, okay, the voltage to your processor is ramping up really slowly. Okay. By our standard, not so much, but the computer standard is really slow. Okay. So you don't want your computer to start to operate until it gets to up to a healthy voltage. So during all that time, the watchdog is going to assert the reset thing that we were talking about. So let me go back to that slide. Oops, not this one, that one. So during all that time, this pin to every component that should be held in the reset state is asserted, which basically is telling the processor, don't do anything. You don't have enough blood supply yet. You're anemic at this point. Don't try to do anything. Is that okay? So once the voltage reaches the healthy level, then the reset pin is released. So all the circuitry will start operating at that time. So that's one function of the watchdog timer. Okay. So the second function of the watchdog is to catch situations where your computer, your operating system has crashed to the point where you cannot even do a control alt delete to restart the computer. Okay, so we don't want to get into those situations, but we do get into those situations, especially in Windows. Even in Linux, sometimes I get into those situations. So now the question is, oh, it's not a big deal. Okay, I just go there and hold my power button for 10 seconds, turn it off, and then turn it back on again, and it's okay now. Okay, so that is true for a laptop computer, or for a desktop computer, even for your phone. Okay, but what if you're operating a data center? What does a data center look like in the inside? You have, okay, first of all, the building of a data center is huge. It makes this campus look small. Okay, so that's the scale of the building itself. Two, you have rows and rows of racks of server computers. Okay, on each rack there are multiple servers that are up and running. Are we good so far? So even if you can identify which server has gone down, okay, and you go in First of all, are you sure you can fit inside, the aisle? Because, the computers are so they try to pack things so densely that sometimes, only robots can reach the server racks after installation. Okay, so there's that problem. Two, you also need people on staff to do that. That's expense. Okay, so we have a lot of issues of, oh, we need a person to go in to cycle power in order to get the computer to start again. So ideally speaking, we want a somewhat automatic mechanism so that when it detects the system has crashed, to a certain point, it would just reset the whole thing by itself. That's the job of the watchdog too. It's the second function of the watchdog. But how does the mechanism work? So the watchdog actually has a timer. Okay, so we'll just kind of imagine the timer to have 5 seconds. Okay, so it's always counting down. Okay, five, four, three, two, one, and so on. Okay, so as long as the timer does not run out, as long as it doesn't reach a zero, it doesn't do a single thing. Okay, then you guys will be asking, but it will get to zero, right? Because five, four, three, two, one, it's just that eventually it will get to zero. Well, you can if you hit the watchdog, then it will reset the counter back to five. So I will say five, four, and then somebody is going to say tech, we're good. Then I will reset the counter back to five. Is that mechanism explained okay? Okay, so I'm gonna use you as an example. By the time I count to maybe three, you will say we're good. Okay, so five, four, five, four. Okay, now now don't say anything. Okay, so now it go like five, four, three, two, one, zero. Okay, nobody tells me everything is good. I assume things have gone really, really bad. Time to reset the computer. That is the other function of a watchdog. Okay, it has a timer that counts down. When it runs out, it will reset the computer. Yep, it is. Your operating system has a timer tick, okay? And the timer tick, would basically hit the watchdog and say, we are good every so often. No, the watchdog is a hardware device. It's a circuit. Yep. The logic to quote unquote hit the watchdog, that is software. And that's the whole point. You're using software to prevent the hardware from resetting. So when the software has gone really, really wrong and it cannot do that anymore, the hardware can now detect that, okay, we're in a really bad situation, time to reset the computer. Okay. So I just want to give you some context of why the reset pin is so important. Okay. So are we still doing okay so far? All right. Cool. So now we're going to go back to Logisim because I want to kind of give you a preview of what we'll be doing from here all the way to the end of the semester. So I'm going to go to a file. Okay, this is the processor file. All right, and I'm going to get rid of these window here. Okay, get rid of that. I will just drag it on the other side. Okay, so this is the processor. Okay, I can zoom out a little bit more. This is the entirety of the processor. And you can see it's a little bit busy, okay? But it is a full processor with RAM, okay? It has 256 bytes of RAM, okay? I don't think anyone in this class has ever had the need to measure single bytes, right? When you guys talk about bytes, okay, oh, my computer has got 32 gigs of RAM. Cool. My hard drive is 2 terabytes. Cool. Okay. I don't think you guys even use kilobytes anymore, or even megabytes. The only time you use megabytes is looking at the image of your photos. It's like, oh, this one is a few megabytes. Okay, cool. And you don't even think of it as any actual substantial amount of storage. Okay, a few megabytes is nothing to you, right? And yet this entire processor only has 256 bytes of RAM. In fact, if I do a right click here and edit content, It opens the window on the other side, but I can move it back here. There we go. That's it. Those are all the locations. Each 00 is a single byte, and this is it. These are all the available locations in RAM for this entire processor. 256. They are used. So this is a good time to illustrate, well, not yet, okay, but this is a good time to at least introduce the concept or reintroduce the concept of, oh, by the way, what is the von Neumann architecture? The von Neumann architecture is basically saying the behavior of the computer can now be specified by the content of these locations, as opposed to, oh, we need to do all the rewiring in order to specify the behavior of the program. The wiring is now fixed. What is going to change would be the content of the RAM locations. Is that okay? All right. And if someone is curious about what kind of program can we possibly fit in 256 bytes, I can say not a whole lot, okay? But I can fit something that actually is in the scope of CISP 430 into this RAM. I can do a binary tree traversal within 256 bytes of RAM. I can also implement the Tower of Hanoi within 256 bytes of RAM. And that's including instructions and also the stack. If you don't understand what the stack means, it's okay. We'll talk about that. That's actually one of the main thing or main topics that we'll be talking about in this class for the next, I would say, starting maybe in 2 weeks or so, 2 or 3 weeks. We'll be talking about the stack. So yes, we can actually write instructions to implement fairly complex recursive algorithms. So here's another word, okay? How many people know what is a recursion or what is a recursive function? Okay, I see a few hands. Okay, I hope the rest of you are just shy because we're going to write a lot of recursive functions in this class. Now, recursion is one of those things where when you learn it in CISP 360, it is almost like magical. It's like, how can this possibly happen, right? In this class, you go like, oh, so that's what's happened. It's so simple. It's not really it's not worth talking about, okay? By the time we are done with this topic, okay? So that's recursion. Um, does everybody know what I'm talking about when I said the Tower of Hanoi? Okay, we got a few people who know it. Most of you probably did not know it, and yet nobody asked me about it. So that's the other thing, okay? When you maybe not yet, okay, but by the time you get to a 4-year university, you have to develop the mental strength to say, okay, if I don't understand something and I think I'm really lost, you need to raise your hand and go like, I don't know what you're referring to. Can you explain what is the Tower of Hanoi? Okay. So the Tower of Hanoi, I can show you a picture and even animated, stuff to explain it. The Tower of Hanoi. There we go. So there are animations to show you how it works, and then this will work. All right, so the Tower of Hanoi, this is actually animated. It shows you how to solve the puzzle. So what it is you have 3 poles. You have all the disks stacked up on the leftmost one, and the objective is to move all the disks all the way to the rightmost pole. Okay, you go like, okay, that's pretty easy. Just take the whole stack, drop it off, and you're done. Well, you have 2 restrictions. One restriction is you can only move one disk at a time. Then people go like, oh, that's easy too. I'll just move one disk at a time to the middle one. Okay, then the whole thing is going to be inverted, and I'll do the whole thing again to the one on the right hand side, and we're done. That's easy too. So this is why the second rule is going to ruin your day, because the second rule says as only a smaller disk can be on top of a larger disk, and you cannot flip the polarity of gravity. I'm just kidding on that one. because then people can go like, oh, okay, now everything is good again, right? Nope, nope, you cannot flip it. So now you go like, oh, so that becomes a little bit of a problem. So the solution is actually in Wikipedia too. So it's not really a complicated solution. So let me see if I can get all the way to the solution, the pseudocode. Ah, come on. Mm, mm. Okay, it doesn't really show the algorithm itself. This is the time complexity of the algorithm. But anyway, the algorithm is not really complicated, but it is recursive, okay? Which means a function is going to call itself, okay? So the processor that we were talking about can do this. And by the way, if you want to know, what is the name of the processor or what is the name of the architecture, it doesn't have a formal name, but I have a name for it. It's called Tax Toy Processor, TTP, Tax Toy Processor. Yep. I think by this time it probably is searchable now. Tax Toy Processor. Oh, I guess I'm curious. Ooh, it's actually here. I am surprised. Likely student work, GitHub topic, and there's an assembler. Okay, all right. So there's some reference, but it's still definitely obscure. Okay, so now the question is, how do I write code to this particular processor? So in today's class, you don't have to write any notes. Okay, the future labs would actually include all the instructions, so you don't have to worry about this. So the assembler, or basically the program to convert code that you write to the machine code that the processor can understand. That's called the assembler in this case. So it is found on the Google Drive, which you already have access to. So let me go back to my drive. Yes, the entire thing. The processor, the assembler, the simulator, the whole tool chain is mine. I'll show you. So you go to the processor subfolder inside the share folder, and then you just double click on assembler, and that is the assembler. You look at this and go like, text, that cannot be an assembler. This is a Google Sheets, it's a spreadsheet, and it really is just a spreadsheet. No, no, I shouldn't say converted, I abused a spreadsheet to do the work of an assembler. So let's go check it out, what it can do. So in here, okay, in this source tab, this is where you put in the program. Okay, the assembly code is different from the x86 assembly code, which is what everybody else use in this class. And I absolutely dislike the assembly code for the x86 architecture for many reasons. Okay, so today's lecture is not about why I do not like that one, but just kind of introduce the tool chain. So this is where your program is going to be entered. I typically put it into a text file and then just copy and paste it into here. And then you would go to the RAM file tab. This is what we need to download. So you go to download, go to CSV, comma separated value, put it into a file. Okay, I'll put it into test.csv, which is already existing because I did it yesterday too. So now we go back to Logisim. Okay, so that's all the way down here. Right click here, load image. So what I just downloaded is called the image file. So now I can go like, okay, go back to that file, CSV, and now you can see the content of RAM, right? Actually, I made a mistake with that program. Let me go fix it so that it actually works right this time. All right, so it's JZI to L2, JMPI to L1, L2 goes here, and then we have a hold instruction here. All right. Okay. Now, since you asked how this is written or in what language it is written, so the answer is it has several things. Okay. So this is called the assembler, and you can see how I intentionally hid a bunch of columns. So when you look at the top cell of a column, it actually contains some of the logic of parsing, the input. Some of the code is actually also in, you go to extensions and then you go to app script. I wrote portions of it in JavaScript. Yes. Yeah, so portions are written in JavaScript. It also has a network connectivity. In other words, you can submit a program to be assembled remotely and then get the assembled version, the opcode back also remotely. So it has web connectivity too, which makes it a little bit different compared to any other assembler. Yep, it's really powerful. It allows you to do a lot of things, and yet you don't have to learn a new programming language because it really is just JavaScript. So anyway, I get back here, and then I re-download the file. Okay, so this right there, call it test.csv, overwrite the original one, go back to Logisim. Okay, in fact, I want to go to where did I go? Oh, right here. Okay, so let me get rid of this. Right click, load image again. Now the program is slightly longer because I introduced two more instructions. All right, so now we can run the program. Um, you won't understand what is happening, but I want to at least show you things that are ticking, changing, and moving so that you guys can go like, oh, okay, we can see that something is happening. So pay attention to register A, okay, which is right here. Pay attention to PC, which is down here. Instruction register, so all of those will change, as we run the program. So we go to simulate, make sure tick frequency is not insanely high. Okay, we make sure that it is something that we can visibly see changes. And then we start the simulation. Okay, so we go ticks enabled, and you can now see how it is running the program. This is a loop of some kind, so it's going to go through the loop a few times. And then after that, it goes to the halt instruction. And when everything is done, the halt pin would light up as a 1, and that means the program has concluded. Okay, so this is how you run the program. All right. So now we pause again. Okay, there we go. Turn off ticks. Okay, there we go. So this is the kind of stuff that you'll be doing pretty much, from I would say about 2 weeks from today, all the way to the end of the semester. What do you need to prepare yourself? How do you prepare yourself by the time we get to this stuff here? First thing first, make sure that your concepts of pointers, dereferencing, structures, all of those things are really clear in your head. Okay, so this would be a good time for me to show you a little bit of the snippet of code that you might be dealing with. Okay, so let me kind of show you some of those items. Okay, so I just go ahead and write a program called test.c. Okay, so now why does it not let me do that? Oh, it's already there. That's why. Okay, abort test1.c. There we go. Okay. So the first thing is you have to get reacquainted with the concept of struct if you don't remember that. So you have to go like, okay, what is a struct and what is M1 and what is M2? So if you have those questions, review those concepts. Okay. Int main, okay, typical stuff. Struct X O obj, okay, object, and then we have asterisk PTR. Okay. So if you look at this and you go like, okay, I know exactly what this means. Obj is a variable of the type of struct X, and PTR is a pointer to something that is of the struct X type. Okay, so if you remember all that stuff, good. Okay, and now if you say, okay, I know exactly what that means. Okay, PTR as a pointer is now storing the address of obj, the variable. Okay, and now we go like, okay, so how do we initialize, the two members inside X? One way to do it is to say, let's say 20. Okay, so if you remember what this symbol, okay, the minus and the greater than, okay, if you remember what that means, excellent. But the other way to do this is to dereference PTR first, so it becomes a structure, and then you can designate a member of that structure. So if you go like, oh, line 8 and 9 are really kind of the same thing. One is really just a eye candy of the other one. So if you get all of these points, then you are kind of ready. Okay. So now to make things a little bit more complicated, okay, we can do something like this, a pointer to a pointer. So now PPTR is the address of PTR, and then we go like PPTR that, and then M2 equals to 5, okay? So if you look at line 11 and you know exactly how to spell it out in English, then you are probably really ready for those topics. So I'm going to give you the answer to this question. Line 11 on the left-hand side of the equal reads as member M2 of the structure that is pointed to by a pointer, which in return is pointed to by PPTR. Okay, now you may not be using exactly the same words, okay, but if you parse what I just said, you go like, yep, okay, cool. That's exactly how I understand this particular construct on line 11, then you're good. Okay, I would say probably a few people in this class understand, how line 11 on the left-hand side of the equal sign works. So if you need some refreshing of those concepts, now would be a good time to kind of ramp it up. Okay, because by the time we get to these concepts, you don't want to ramp up at that time. Okay, you want to do it prior to that time. Are we good so far? So how many people look at this code and go like, yeah, I'm pretty sure I can figure this out by the time we talk about it. Okay, that's good. Okay. So all right. So I'm glad that you guys feel confident that you'll be able to understand this code by the time we get to that, because what we'll do is we are going to implement this kind of code in assembly code using text toy processor. Does anyone know how we are going to debug the program? Do you even want to know? What? Yes. So when we run the code, we can run it in Logisim with a full trace of what instruction executes, what changes, what register, all the updates, everything can be logged. So the tool, okay, I will even give you an idea. We still got about 3 more minutes before the promised end time. So what I'll do is I am going to give you an idea of what tools are available. Okay, so document CISP 310, Reaver Spider, submit, temp, test.ttp.asm. Okay, so this is a script that I wrote. Okay, it is made available to all of you, and it will run in Linux, it will run in Mac OS, it will also run in Windows. Okay, so I got all three versions covered. You press this key, it will do all that crazy crap for you. Okay, but it will do one more thing. Okay, so we'll let it do it. It takes a little bit of time because it's using the web interface of the script that we talked about. It is called a web app. Okay, in Google App Script terms, it's called a web app. So it's making a connection to the web app. Okay, there we go. So it will even give you some minimal feedback. Assembly is done, object code is good, simulation is now done, and then the trace data is now uploaded. So now when we go back to the spreadsheet, like this, okay, there's a tab called analysis. So the analysis tab, this is not actually the program that we wrote, because I think I forgot to save it. Anyway, it is showing you the full execution of the program. Okay, this is something that a debugger cannot possibly do, because it's showing you for every single instruction that executed, what are the side effects, which register got changed in what way, by which instruction, at which location. So it gives you the full history of the execution of the program. Okay, so that's our main debugging tool. It's also a visualization tool so that when we get to the concept of a stack pointers and stuff like that, they are all spelled out here. And this is really just a regular Google Sheets. So that means, when you get here, okay, the next I would say about 3 laps, 2 to 3 laps from today, you'll be doing this. You can go to this thing, go to make a copy, and make as many copies as you want. Okay, so that means for every program that I write, or for every program that you will write, you can have a different file. And then in that file, you can also add your own comments any place you want. So this is a tool that gives you the visibility of what happens when these programs run, and therefore you have a way to not only understand or visualize what is happening, but this is also a medium where you can take your own notes, write down your own comments, okay, annotate anything that you want. Okay, so that's kind of the resource that I will be providing. Okay, and I hope you guys will make use of that if you think it is helpful. So that's the end of today's lecture. I just want to give you an overview of what we'll be doing and what you need to kind of study in order to get ready for that part. All right, so I'll see all of you, most of you, next Tuesday. Have a nice weekend, because some of you are in Mesa and I'm the chaperone. Yep. Yes. So those people will see me, unfortunately, on Saturday as well. There's no escape. It's the weekend. I don't want to see tech over the weekend. Here I am. All right. Let me turn off the recorder.